Question 12 from Paper 2 of the 2024 Higher Physics Examination from the SQA. A student is investigating refraction of light using the apparatus shown. You've got a semicircular perspex blocks. You've got a ray of light coming from a laser aimed at the centre of the perspex block, and we know what's going to happen. The ray of light is going to be refracted in this particular direction here. It goes a straight line because it's travelling along a normal, because from the circumference point here to the centre of the circle is a normal, and therefore the ray of light travelling along a normal doesn't change direction. So the ray of light comes in and it bends in this direction here. Now we've got to suggest how the student's measurements should be processed to find a reliable value for the refractive index of perspex for the light from the laser. Well, you would measure the angle of incidence here, that's angle I, and that would be the angle of refraction R, always between the ray and the normal, always between the ray and the normal. And you take a series of measurements of angle I and angle R for different incident angles, and you'd end up with a table like this. I've just made up these just kind of like showing you a typical table you'll have and show you the process you would have to find. So you can see from that you have got a series of results: theta I 20 degrees, theta R 13 degrees. You would measure the next one, 30 degrees, and theta refracting 19 degrees. That wouldn't really tell you anything, but if you went to sine theta I and sine theta R, you would get these values here. And then if you look close enough, if you take the ratio sine theta I divided by sine theta R, and you did the ratio of these ones, you would get a value of 1.50. I've just given you an example of that to show you the process you would take, and that would be equal to the refractive index of the particular perspex block. So you would take your angle of incidence, you would measure it, you would take the angle of refraction, you would measure it, and then you would take the sine of those two values, and then you look at the ratio, and you always get a constant number, and that tells you an important thing, that sine theta I over sine theta R equals a constant number, and that constant number is the refractive index. Now there's a second way you can do this. You could plot the points again like this. You could have sine theta I along the way in the x-axis. We'll just call that an x-axis for the moment. And the y-axis you could have sine theta R, and you would get your lines like this. You would get a kind of constant kind of line like that. I'll draw it in for you. You would get a line from the origin going through, the best fitting line all the way through that. That tells you a very important thing. It tells you a relationship between sine theta R and sine theta I. We can say almost that from this, if it passes through the origin, it's a straight line. We can say that sine theta R is directly proportional to sine theta I. Now we can then say that sine theta R, remember that's the y part there, we can say that the y part is got to equal to a constant times the x part, which is the sine I here. So really the constant would be the gradient of this graph here, but that wouldn't be the refractive index, because you worked out the gradient of that graph. Remember, this is the delta y, the gradient, that's delta x. So your gradient is going to be, gradient m is going to be sine theta refraction divided by sine theta incident, if you work that out. And that's not going to give you the refractive index, it's going to give you 1 over the refractive index. So depending if you do the more complicated graph version, you have to plot the straight line, have to know that sine theta I is the one you're changing, sine theta R is this variable up here. The gradient is going to be sine theta R, difference in sine theta R, divided by the difference in sine theta I, which is going to give you 1 upon the refractive index. But the best way to process results is to use your table, get the ratio, sine theta I divided by sine theta R is 1.5, and that's the refractive index. That'll give you 2 marks. Question 12, Part B. The student determines the refractive index of the perspex block for this light to be 1.50. And for 3 marks we have to calculate the critical angle of perspex for this light. Well, the critical angle, sine theta C, from the relationship sheet, sine theta C is going to be equal to 1 upon the refractive index. So sine theta C is going to equal to 1 divided by 1.50. And we put that into our theta C, that's equal to the inverse sine minus 1 of 1 over 1.50. Do that with a calculator, and we end up with an angle of 48.1 degrees. Question 12, continued part C. The student now directs the ray of light into a perspex block as shown. You can see the angle of incidence there is 50 degrees, and we're asked to find out, complete the diagram to show the path of the ray of light after it's incident on the perspex air boundary. And we have to mark on the diagram the values of all relevant angles. Well, in the previous part of the question, we found out that the critical angle, theta c, was going to equal to 48 degrees, 0.1 degrees. So 48.1 degrees. Now, what does that mean? It means that any angle bigger than 48.1 degrees inside the perspex is not going to come out the perspex block, but going to be internally reflected. So what we have here is this situation. We have the ray of light coming in, 50 degrees, bigger than the critical angle, and therefore it's going to reflect in that direction there. It's asked you to put in all the relevant angles, and we know that the angle in here is going to be, the angle of reflection is going to be 50 degrees. So we're going to have a 50 degree angle here like that, 50 degrees in there. And that's because the angle here in the perspex block, 50 degrees, is bigger than the critical angle. Therefore you'll not get the ray coming out into the air. It will be internally reflected along this way here. It will not change direction, but as I said before, from the centre of the semicircular glass perspex block to out to its circumference, that is a radius, and that is a normal, and if the ray of light is travelling along a normal, and if a ray of light travels along a normal, it doesn't change direction. So you only put one angle in there, and that's 50 degrees, total internal reflection.